So this is the activity for Chapter 17, the special senses, and we're going to walk through the different questions on the in-class worksheet. So we'll start with Part 1, Olfaction and Gustation. More than 2.7 million Americans have a problem with olfaction, although this is likely an underestimate. Olfactory dysfunction can even be an early symptom of some other neurological diseases such as Parkinson's disease. Some medications and drugs like tobacco can also diminish olfactory ability. Unfortunately, olfactory ability also decreases with age. A damaged sense of olfaction can be severely disrupting. About 1.1 million Americans report a problem with gustation, although approximately 80% of taste disorders are truly smell disorders. Unfortunately, smell and taste disorders are often overlooked in most aspects of medical practice. Therefore, much about the diagnosis and treatment of taste and smell dysfunction remains to be discovered. So number 1, what are some similarities between olfactory and gustatory receptors? Well, both are specialized types of chemoreceptors that detect chemicals in the air in case of olfaction, and chemicals in food and drink in the case of gustation. In both cases, the chemicals are first dissolved into an aqueous solution before binding to a receptor. Airborne molecules dissolve in the mucus in the nose, and molecules in food and drink dissolve in the saliva in your oral cavity. They both also involve changes in the membrane permeability to ions, which results in a graded receptor potential. They also both have G protein receptors, which activate signaling cascades. Those we'll see in a moment, gustatory receptors actually have a second type of receptor as well. They both have extensions to increase the surface area for the receptors. Olfactory receptors have the dendritic bulb with cilia that extends out into the nasal cavity, and taste buds have microvilli that extend out into a taste pore. So number 2, what are some differences between olfactory and gustatory receptors? One of the differences is the structure of the primary receptor. In the olfactory system, the cell with the receptors itself is a modified sensory neuron, where with the gustatory system you have a separate receptor cell called a gustatory cell that's located in the taste buds, and these cells are then monitored by sensory neurons, but they are not themselves sensory neurons. The mechanism of the receptor is also different. They both have the G protein receptors, as we talked about in the previous question, but with olfactory, it is only a G protein receptor, so it is the indirect signaling. The chemical binds to the G protein receptor and starts a signal cascade that then will eventually cause a change in membrane potential, whereas with the gustatory, it also has that system, but it also has ion channels that directly allow ions to pass the membrane and change the potential. That is the case of the salty and the sour senses. They also differ in the number of different types of receptors. With the olfactory system, there are at least 50 different primary smells. So there's 50 different G proteins that all bind to different chemicals in the air. With the gustatory system, there are only 6 different receptor types: sweet, sour, bitter, salty, umami, and water. The location is also different. In the olfactory system, the special sense organ is in the nose, so the receptors are in the olfactory organs in the nasal cavity. In the gustatory system, the receptors are located in taste buds, which are inside 3 of the 4 types of lingual papillae, which can be found on the tongue. And then the destination of information in the central nervous system is different. Olfactory information goes straight to the olfactory cortex, and it bypasses the thalamus completely. It also goes to limbic areas and to the hypothalamus. Gustatory information goes to the gustatory cortex, and it is filtered by the thalamus before it gets there. Number 3, the majority of reported taste problems are actually smell problems. Explain why this is, and explain all of the sensory input that arises from putting something in your mouth. So when you eat or drink something, Some of the chemical molecules vaporize and pass through the pharynx into the nasal cavity. So the nasal cavity and the oral cavity are connected to each other through the pharynx. So when they get into the nasal cavity, they can be detected by olfactory receptors, and we actually have a name for this. It's called retronasal olfaction. So here is an image to again show you that you have your oral cavity down here, you have your nasal cavity up here, and they are connected in the back by the pharynx. So when you breathe in air molecules which then pass by your olfactory organ, but when you breathe out, different molecules that are present in your oral cavity from the food and drink you're eating can also go up and activate the receptors in the olfactory organ. So olfactory information is therefore a large part of what we perceive as the taste of something. And we know this because if we have a cold and our nose is blocked, food doesn't taste as rich as it usually does. It can be somewhat bland. And so children will also take advantage of this by holding their nose when they're trying to eat something that they don't like. In addition to the gustatory information from the taste buds and the olfactory information from the olfactory organ, taste also involves tactile receptors on the tongue, which send information about texture. So is something crunchy, soft, rough, smooth, silky, etc. Thermoreceptors send information about temperature. So is the food you're eating hot, warm, cold, lukewarm, etc. And you even have nociceptors that send information about pain. So as I mentioned before, the hot, spicy chili peppers have a chemical called capsaicin in them that stimulate the nociceptors as well as the noxious thermoreceptors for heat. And so that spicy hot feeling you get is actually a combination of pain and temperature. So in part 2, we're going to look at a case study that's called Eric Can't See. And we're going to start with the intro. It was a sunny day in 2005 and time for Eric's annual eye exam. "You know," says Dr. Tim, "we really should measure your visual fields. It's been at least 10 years since you had that done." "I hate them," Eric grumbled. "I get disoriented, and anyhow we already know I have a large blind spot." Eric raised his hand, squinting through one eye. "Here, I can't see my finger here." "I know," Dr. Tim was sympathetic, "but weren't you just telling me you haven't seen stars for a while? It's important." An hour later, Eric was seated in front of a large white screen, staring intently at a light in the middle. "Keep looking at that light so your eyes don't move. If you see another light anywhere else, push this button." Eric began the test by focusing on the light he saw in the center. The machine then successively displayed points of light of varying intensity in different places around the entire visual field. When Eric saw the peripheral light, he pushed a button. He did his best to detect the flashes, but realized he was probably missing some. The machine mapped out where he could see and where he could not. So number 1, as the light from the machine passes through Eric's eye, list the anatomical structures that it passes through in order, beginning with the cornea and ending with the photoreceptor. Include any cavities and indicate which type of eye fluid is found in that cavity. So I've got a little unlabeled picture here that we can use as we walk through the different structures that the light will pass through. So the first structure the light will pass through is the cornea, which is this outermost point on the anterior surface of the eye. Then the light will pass through the anterior cavity, which is between the cornea and the lens. And the anterior cavity is full of a fluid called aqueous humor, which is a very watery type of fluid. Next, the light will pass through the pupil. And remember, the pupil is the opening or the hole in the iris. The iris in this picture is shown by these two little green flaps. And then the light will pass through the lens. Then the light will pass through the posterior cavity, and the posterior cavity is full of the vitreous body, which is a gelatinous mass that does have some fluid called the vitreous humor. There is also a small amount of aqueous humor in the posterior cavity, but the largest part of the posterior cavity is taken up by the vitreous body. and then the light will hit the photoreceptors that are present on the retina, which is at the back of the eye. Number 2, after the photon of light hits a photoreceptor, describe the pathway that the sensory information follows, beginning with the photoreceptor and ending with the visual cortex. Where else in the brain does the light information go, and for what reason? So I have two little pictures here. I have a picture of all of the cells that make up the retina up here in the upper left, and then I have a picture of the different pathways through the brain on the bottom right. So we start with the photoreceptors in the retina, and remember we have two types, rods and cones. Information will be passed from the photoreceptors to the bipolar cells, which is the next layer of the retina. The bipolar cells will pass the information to the ganglion cells. All of the axons of the ganglion cells will come together to form the optic nerve, which is cranial nerve number 2. So now we can also move over to this picture, and we see the optic nerve coming out of the back of the eyes. The optic chiasm is the point where some of the axons are going to cross over, so that all of the left visual field ends up on the right side of the brain, and all of the right visual field ends up on the left side of the brain. After the optic chiasm, we call that pathway the optic tract. Then the information is going to pass through the thalamus, where it's going to be filtered and relayed. And specifically, visual information travels through the lateral geniculate nucleus of the thalamus. And then from the thalamus, it's going to be sent to the primary visual cortex in the occipital lobe. And then to answer the second part of the question, where else in the brain does the light information go? Light information is also going to be routed to the suprachiasmatic nucleus of the hypothalamus. So there'll be a branch of the optic tract that will take information here. And this helps the suprachiasmatic nucleus to maintain our circadian rhythms, our day-night cycles, and in some animals, their seasonal rhythms as well. And the SCN also inhibits the pineal gland when it senses light and stops the pineal gland from producing melatonin. So melatonin is only produced in the dark. Visual information also goes to the superior colliculus, which is part of the tectum on the posterior side of the brainstem. This is part of our visual reflex system. The superior colliculus will control unconscious eye, head, and neck movements in response to visual stimuli. Number 3, Eric's field test results for his left eye are shown below. Both eyes were the same, so we're just showing one eye. And it's compared to the results of a normal eye. The black spots indicate lost vision. What do you think the black spot represents on the normal eye's result, and what causes this feature? What could you conclude about Eric's vision? So this is that test they give you at the eye doctor, where they have flashes of light going on in the little machine, and you press a button every time you can see the flash of light, and then it maps out the different part of the retina that should have received that light, and if you were able to see it, then it's going to be a white area on the result. If you weren't able to see the flash of light, it's going to be a black area on the result. So let's take a closer look at the normal eye, and the question asked you what was this black area on the normal eye. This black spot on the normal eye represents our blind spot. This is the location of the optic disc on the retina. At the optic disc, the axons of all of those ganglion cells are coming together to form the optic nerve, which then passes through the back of the eyeball. And since there is no room for photoreceptors in this area, any light that falls in this area cannot be detected. So when the flash of light falls on this area, you won't press the button because you won't see it. So then let's take a look at Eric's results. So Eric's results show that he is only able to detect light in the very center of his visual field. The black all around the edges means that Eric has lost his peripheral vision. So he has his central vision, but no peripheral vision. So now we're going to look at part 2, which is the diagnosis. Dr. Tim looked at the printout. His face grew serious. Eric, we have a problem. You have limited peripheral vision, and it's bad enough that I don't think you should be driving. This looks to me like something called retinitis pigmentosa. We should refer you to a specialist. Dr. Paul, the retina specialist, folded his hands. I'm afraid you do have retinitis pigmentosa. It's really a syndrome with more than 70 known genetic mutations that can cause it. But in all cases, the pigments lining your eyes gradually break down, so you can't sense the light that hits your eyes. Eric winced. Great. So what do we do about it? Dr. Powell shook his head. Not much, I'm afraid. One study has shown that taking vitamin A may slow the rate of loss, but the loss is irreversible. Typically, patients slowly lose their peripheral eyesight at a rate of, say, 5% loss per year. The speed can vary enormously, and in many people it can slow or simply stop. But in other cases, patients do become blind. So number 4, explain how a pigment molecule is essential to the process of photoreception. Then review the 4-step process of photoreception. So pigment molecules are membrane proteins that contain a molecule of 11-cis retinol in the middle. So here's a representation of a pigment molecule. So the gray area here would be the plasma membrane. So we have in this light purple, this would be the membrane protein called an opsin, and then embedded in the middle of the opsin is a molecule of retinol. Pigment molecules are essential for photoreception because they are responsible for absorbing the photons of light, which allow our bodies the ability to sense light. So they're key in turning that light signal into an electrical signal. When a pigment molecule absorbs a photon of light, the light energy changes the 11-cis retinol into 11-trans retinol. So in the inactive form, the protein has an 11-cis retinol buried inside of it. Then the energy from the light photon converts that to 11-trans retinol, and that conversion causes the protein to change shape, which activates it. So this changes the shape or activates the pigment molecule, which then allows it to interact with other molecules. So in this kind of a cartoon figure here, you can see that in its activated state, opsin now has a little pocket where it can interact with other molecules, specifically one called transducin. So let's review the 4-step process of photoreception. First, remember that at the resting state, in the absence of light, photoreceptors have sodium channels that are being held open by cyclic GMP. So in a photoreceptor in the dark, you actually have sodium coming into the photoreceptor and depolarizing it, and we call this a dark current because it's happening in the absence of light. So now let's look at the 4-step process of photoreception, and we're going to use this little picture to help us as we go through the 4 steps. So step 1, opsin is activated. The photon of light will convert the 11-cis retinol into 11-trans retinol, which again is going to change the shape of the opsin, thereby activating it. Step 2, the activated opsin activates a molecule called transducin, which then in turn activates a molecule called phosphodiesterase, or PDE. So step 2 is this signal cascade. Activated opsin activates transducin, which activates PDE. Step 3, the activated PDE breaks down the cyclic GMP that was holding the sodium channels open. So when that cGMP is broken down and there's no more of it around, the sodium channels will close. So step 3 is reduction in cGMP, and the closing of the sodium channels. And then step 4, the dark current stops and the receptor potential becomes more negative. So when the sodium channels close, the flow of ions, which is what we call a current, so the flow of sodium stops, and sodium is no longer coming into the cell, so the membrane potential of the receptor becomes more negative. So we can say it hyperpolarizes, which is going to cause the receptor to stop sending a signal to the bipolar cell. So step 4, the dark current stops, the receptor potential becomes more negative, and the photoreceptor stops sending a signal. Number 5, given that Erich's pigment loss is primarily in the periphery, what type of pigment molecule and what type of photoreceptor do you think is primarily being affected? Well, in the retina, the cones are concentrated in the center area around the macula, and specifically in the fovea centralis, which is cones only. And then rods are going to be more prevalent in the periphery. Since Erich's vision loss is in the periphery, then his condition is affecting the rods, which contain the pigment molecule rhodopsin. Number 6, given your answer to question number 5 above, would Erich have more trouble seeing during the day or at night? Why? Erich would have more trouble seeing at night and in low light conditions. So the rods are highly sensitive to the presence or absence of light, so they enable us to see in low light conditions like a dimly lit room, at twilight, when there's only a moon in the sky, etc. Cones give us our color vision and our sharper, more crisp images, but they require bright light to do so. So in this particular little graph here, it shows the luminescence, or how bright certain things are. You can see that cones work best in bright situations, whereas rods can sense light in cases of where cones cannot. So given that he has a problem with his rods, he's going to have more trouble seeing at night. Number 7, why would the doctor suggest taking vitamin A to slow the progression of Erich's disease? So first I'm going to show you this little pathway, and it might look complicated, but don't panic, it's pretty simple. So when you buy vitamins and supplements and they say that they have vitamin A in them, there are 2 primary types that you're probably buying. There's one type called beta carotene, and there's another type called retinol with an O, so an OL instead of an AL. And on the supplement bottles, the retinol probably says retinol acetate or retinol palmitate. So this is the vitamin A that we take and we eat. And as you can see, both the beta carotene and the retinol with an OL can be converted into retinol with an AL. So both of these can be converted into 11-trans retinol, which is then converted into 11-cis retinol, which is the molecule that is used by your photoreceptors. So because retinol with the AL is required for the pigment molecules to function, making sure you have enough vitamin A in your diet, which is shown by these 2 lighter orange boxes, can promote healthy vision, because both of these supplementary forms can be converted to retinol with an AL. In this section, we're going to look at the feelings. Below is a poem that Erich wrote about pigmentosa. At the time, he was coming to grips that he really had a vision problem. Retinitis pigmentosa. I lie in bed and gaze into the universe's soul through my skylight. The refracted blue curtain has been pulled. Her Serenity the moon is visiting China. The sky overflows with starlight traveling long decades for this moment. But I cannot see the stars. Shadow on shadow, shades of purple and gray. Dimly I see a dark window edge. And there, trembling on the edge of awareness, yes, there, straining to fix her, triumphant, I find a star. It is probably Venus, but I am pretending. Oh, I know they are there. I remember that shimmering pale blaze, remember their gleam as an old man remembers long-lost lover's touch. If you were here, you would share your vision. No, I will not shed tears for lost sight again. I mumble my prayer, I thank you, Lord, that I do not have macular degeneration. My selfish depravity swells and I am ashamed. A single tear slips to water my beard. Must be allergies. So number 8, why can't Eric see stars? So remember that our ability to see stars relies mainly on our rods, because stars are very dim lights that are only visible in the night sky. So the starlight is actually technically still there during the daytime, but because the sun is so much brighter, we can't see the dim lights of the stars during the day. And did you know that people who live in or close to large cities also can't see the stars because the city lights are too bright and block them out? So starlight is a very dim type of light, and you need rods to be able to see starlight. So with retinitis pigmentosa, it is the rhodopsin and the rods that degrades first, so the ability to see dim lights like stars will decline and disappear. Number 9, in the last stanza, Eric sheds a tear. Describe the flow of tears from production to elimination. Use the figure below to show the pathway. What are the functions of tears other than as a part of an emotional reaction? So tears are produced by the lacrimal gland. You have one in each eye, and they are on the superior lateral surface of the eye. They are secreted through these tiny little lacrimal ducts, and then they flow over the ocular surface of the eye, and this is helped by the process of blinking. They then gather at the medial angle of the eye, also called the medial canthus. They then drain into 2 small pores called lacrimal puncta, and you can see the tiny pores here in black, and then I'm going to highlight them so you can see them a little bit better. And then they flow through these 2 lacrimal canaliculi, which are tiny little canals. And then they're going to gather together into the lacrimal sac. They're going to pass through the nasolacrimal duct. And then finally they are excreted into the nasal cavity. And this is why you get a runny nose when you're crying, because the excess tear volume is being drained into your nasal cavity. And then the second part of the question, asking about the function of tears. Tears help to reduce friction. If you've ever had dry eyes, then you know you can feel your lids blinking. It feels gritty and rough, and it can hurt. Tears also remove debris from the eye. They prevent bacterial infections because they contain antibodies and lysozymes. They provide nutrients and oxygen to the outer epithelial layers of the eye. So dry eyes are a common occurrence. They can be caused by things like the dry environment, the cold, sun exposure, smoking, wearing contact lenses, certain allergy medications, and then heat or chemical burns. And when you have dry eyes, you're basically not getting the normal functions of tears. So this can cause, like I mentioned before, it can cause your eyes to feel rough and sore. They can be itchy. They can feel really heavy and tired. And so they do make eye drops for dry eyes. And then if it's a chronic problem, you can see your doctor for other types of solutions. Number 10, critical thinking. There is another eye disorder called blind sight. In people with this disorder, there is nothing wrong with the photoreceptors, visual pigments, or the eye itself. But for all intents and purposes, the person is blind. However, these individuals seem to be unconsciously aware of their environment without being consciously aware. They would tell you that they can see nothing, but if you threw an object at them, they would reach out and catch it, all the while denying that they saw the object. Can you suggest a possible explanation for this phenomena based on what you have learned in Chapter 17? So for us to have conscious awareness of what we see, the visual information has to be processed in the primary visual cortex of the occipital lobe. So people who have damage to their primary visual cortex in the occipital lobe are functionally blind. They will tell you they can't see anything because they have no conscious awareness of receiving any visual input. However, in these cases, their eyes are still functional and their eyes can still receive visual signals. The problem in these particular types of blind patients are that their visual cortex is damaged, and we call this cortical blindness. So we differentiate between blindness caused by a problem with the eyes and blindness caused by a problem with the cortex. And so this is a type of blindness called cortical blindness because the problem is with the visual cortex. For example, it could have been damaged by a stroke or an accident. So even though the visual information is not getting processed by the visual cortex, it still goes down those other pathways we talked about. It still gets sent to the superior colliculus, it still gets sent to the hypothalamus, it still gets sent to the thalamus, copies get sent to the cerebellum to help with equilibrium. And so people can, quote, still see stuff, but it's on a totally unconscious level that they are not aware of. They'll tell you they don't see anything. And this is called blind sight. In one famous case, a man who had cortical blindness was told to walk down a hallway. He was told the hallway was clear, but they actually put obstacles up and down the hallway. And he was able to subconsciously avoid all of the obstacles without being aware of it. And he would tell you, I don't see anything. I'm going to put a video on D2L if you're interested in learning more about blind sight. It is quite a fascinating condition. So this is part 3, a case study called Why Does Grandpa Ignore Grandma? While listening to a lecture on the auditory response, Carla thought back to a specific event that had occurred the previous Christmas involving her grandparents. Grandpa Carl was a calm and loving man who spent his working career as an auto mechanic in the small northeastern Wisconsin town of Marionette. Grandma Marie was a 5'1" ball of fire with a high-pitched shrill voice who always wanted to accomplish more than was physically possible in a day. The only time she relaxed was when she slept. Grandma and Grandpa lived 8 miles west of town in a 2-story house with a wraparound porch on a 160-acre farm. During that Christmas event, Carla and her mom prepared dinner under the watchful eye of Grandma Marie, while Grandpa Carl and her dad sat in the living room watching the Green Bay Packers play the Chicago Bears on TV. Carla almost laughed out loud in class as she remembered the situation. Grandma Marie: Daddy, would you take the garbage out to the trash can? Grandpa Carl, not responding to Grandma: Wow, Bob, did you see that play? I don't think he caught the ball. I bet this one will be challenged. Grandma Marie, her voice a bit more shrill: Daddy, I told you to take the garbage out to the trash can. Now get out of that chair and do it. Grandpa Carl still does not respond. Grandma Marie, turning to Carla: He never listens to me. Every time I tell him to do something, he just ignores me. Carla: I don't think he can hear you, Grandma. He's pretty far away and the TV is going. Grandma Marie comes into the living room behind Grandpa Carl, trying to remain calm. Daddy, I asked you to take the garbage out to the trash can. Now please get out of that chair and do it. Grandpa Carl, noticing Grandma, turns around and then turns and looks at Bob with a confused expression on his face. Bob, calmly: She would like you to take the garbage out to the trash can. Grandpa Carl: Oh, okay. He gets up and heads to the kitchen to get the garbage. Grandma Marie, now furious, screaming at Grandpa: You'll listen to him, but you won't listen to me. I don't know why I have put up with you for the past 54 years. Grandpa Carl calmly heads to the kitchen to get the garbage, confused by Grandma's frustration. So number 1, trace the path of sound from the outer ear to transmission by the vestibulocochlear nerve, detailing what happens at each step in the pathway. Make sure to discuss all of the structures involved. You can use the figure below to help you trace the pathway. So I'm putting the figure up here at the top, and we'll walk through the numbers as they are listed on this diagram. So number one, the sound waves enter the ear and they pass down the external acoustic meatus. When they come into contact with the tympanic membrane, it's going to start vibrating in resonance with the sound waves, meaning that it's going to match their frequency and amplitude. Number two, the movement of the tympanic membrane moves the malleus, which moves the incus, which moves the stapes. Number three, the movement of the stapes at the oval window establishes fluid pressure waves in the perilymph of the scala vestibuli. Number four, the pressure waves pass over the basilar membrane at a point matching the frequency of the sound waves, causing the basilar membrane to move up and down at that point where it crossed over. Number five, the vibration of the basilar membrane pushes the hair cells of the spiral organ up against the tectorial membrane. Number six, the bending of the cilia of the hair cells causes an electrical signal which is passed along sensory neurons that make up the cochlear branch of the vestibulocochlear nerve. Number two, how does the brain know the frequency of the sound heard? How does it know the intensity or amplitude? So the frequency is determined by the area of the basilar membrane that the pressure waves are going to cross over. Different frequency sounds cross at different points along the basilar membrane. Higher frequency sounds are going to cross closer to the base of the cochlea where you have the oval window, and lower frequency sounds are going to cross closer to the apex or the point of the cochlea. So if we look at this image over here, so the cochlea is shown in this snail shell shaped, and the organ of Corti is where the hair cells are located, also called the spiral organ. So higher frequency sounds are going to be closer to the base, lower frequency sounds are going to be closer to the apex. And the same map of frequencies is also found in the auditory cortex. So the different areas of the basilar membrane are mapped across the primary auditory cortex. And the intensity of the sound is determined by the number of hair cells activated and how strongly the hair cells are activated. So louder sounds are going to activate more hair cells, and it will also push those hair cells that it does activate more forcefully against the tectorial membrane, which will cause the cilia to bend more and open more ion channels. Number three, why do you think Grandpa Carl could hear Bob when he couldn't hear Grandma Marie? Hint, look at the graph below that shows age-related hearing loss. So what this graph is showing, down here is the different frequencies, so lower frequencies on the left, higher frequencies on the right. And this axis over here is showing the hearing loss, and so at 0, that means there's no hearing loss. And then the different lines represent the different ages. So at age 20, there should be little to no hearing loss. At age 30, you've lost some sense of the higher decibels. At age 40, again, mostly in the higher region, and then 50, and then 60. And so what you can notice by this graph is that as you get older, you're going to lose your ability to hear high frequency sounds, while the ability to hear very low frequency sounds stays pretty much intact. So Grandma Marie had a shrill, high-pitched voice, meaning that she spoke at a higher frequency than the lower pitched tones of Bob. So therefore, age-related hearing loss would have meant Grandpa Carl would have had a harder time hearing higher pitched voices, such as Grandma Marie's. Number 4, what type of mechanism could explain Grandpa Carl's hearing loss? So age-related hearing loss usually involves cumulative damage to the hair cells of the cochlea. The hair cells closest to the oval and round windows at the base are damaged more because they're used more, and these are the hair cells responsible for detecting high-frequency sounds. Grandpa Carl also worked as a mechanic, so he was probably exposed to a lot of high-pitched, loud machinery sounds during his career, which would have accelerated his hearing loss. So here is an image showing you what normal hair cells will look like inside the cochlea. Then when they get damaged, the cilia become disorganized and disarrayed, meaning that they no longer can function the way they normally do. And then with severely damaged hair cells, you actually even lose hair cells altogether. So here's my little PSA about taking care of your hair cells. Hair cells do not regenerate, so if you lose them, they're lost forever. And it's a big concern nowadays with headphones and earbuds, and people tend to listen to their music too loudly. And notice that frequent exposure to sounds over 70 decibels can cause hearing problems and hearing loss over time. And the louder the sound, the quicker it can cause damage. So here is a chart of different sound levels and how it affects your hearing. And notice that personal listening devices such as headphones and earbuds can go all the way down here into this danger area, in which you can have hearing loss possible in less than 5 minutes time. So one good rule of thumb: if you can hear your music while holding your earbuds or headphones at arm's length away, your music's probably too loud. And you should try limiting your music device or headphones to 60% of the maximum volume, and take breaks every hour. So take care of your hair cells. They're the only ones you get. Number 5, describe the structure of a hair cell. How can this one receptor be responsible for sensing gravity, acceleration, rotation, and hearing? So here is an image of a hair cell, and then I like this because it shows you a scanning electron image of a hair cell, so you can actually see what a real hair cell looks like that's been magnified many times. So you can see all of these little stereocilia that stand up on top and are clumped together. So hair cells are receptors with stereocilia on their free apical surface. The stereocilia range in length. Some are shorter than others, with the kinocilium being the longest one. When the stereocilia bend in the direction of the kinocilium, so when they bend in the direction of the longest stereocilia, the ion channels are opened. And so these little cilia are actually connected to each other with proteins. So when you bend them in one direction, it opens ion channels, and when you bend them the other way, it closes the ion channels. So when the ion channels open, this causes depolarization, and this is going to send a signal to a sensory neuron. When the stereocilia bend in the direction away from the kinocilium, the ion channels will close. This will cause hyperpolarization, and this will stop any signals to the sensory neuron. And again, here is an image showing you what damaged hair cells look like compared to normal hair cells. So the stereocilia are no longer clumped together, so they no longer can bend together in an organized fashion in one direction or another. And sometimes even the random bending of these cilia can cause a sensation of ringing in your ears, which is also called tinnitus. So let's look at the second part of the question. So this one receptor can be used to sense equilibrium and sound because of the way it's positioned within different structures within the inner ear. So the different structures allow the cilia of the hair cell to be bent based on these different stimuli. So if we look at gravity and acceleration, this is sensed in the vestibule, and the hair cells are embedded in a gelatinous otolithic membrane with tiny little stones called otoliths sitting on top. And so the cilia of the hair cells are bent with the force of gravity or acceleration. With rotation, the hair cells are located in the semicircular canals. They're embedded in a gelatinous substance called a cupula. Rotation of the head causes fluid to move around these canals. The fluid pushes the cupula, which bends the hair cells and sends a signal. And then with hearing, we have hair cells in the spiral organ of the cochlea, and the hair cells are sitting on a basilar membrane. And then when the basilar membrane moves, that pushes the hair cells up against an unmoving tectorial membrane by the sound waves, and that bends the cilia and sends a signal. So because of the way that the hair cells can be bent, the cilia can be bent in different ways, allows it to for us to sense gravity, acceleration, rotation, and hearing. Number 6, conductive hearing loss occurs when the sound waves are unable to reach the cochlea. What structures could be damaged in conductive hearing loss, and how might they be damaged? So with conductive hearing loss, the structures of the inner ear, the cochlea and the hair cells, they're fine, as shown by the green arrow. But the problem is getting sounds to the inner ear. So with conductive hearing loss, we have some type of problem in either the outer ear or the middle ear. So some examples that could cause conductive hearing loss include blockage of the external acoustic meatus, like with a buildup of earwax or something has been inserted into the ear. Rupture of the tympanic membrane. This can happen with infection or in sudden changes of pressure, like with diving or skydiving or diving underwater. Ossification or other immobilization of the auditory ossicles, which can happen from disease or trauma, and that means the little bones are unable to move, which means they can't pass the sound along. You can also get fluid that accumulates in the middle ear. This can happen because of colds, allergies, or infection. Remember, the middle ear is connected to the nasal cavity through the auditory tube. And so those are all ways that you can end up with conductive hearing loss. So number 7, sensorineural hearing loss occurs when the hair cells are damaged, when there is a problem transmitting the sensory information to the brain, or there is a problem with the processing ability of the brain. So trace the pathway that auditory information follows once it leaves the hair cells. So here is a little picture that we'll use as we trace the pathway. So we start with the hair cells in the cochlea. They're the ones that are going to send the initial signal. They then pass that information to the cochlear nerve. The cochlear nerve joins up with the vestibular nerve to make the vestibulocochlear nerve, which is also cranial nerve number 8. This is going to carry the information to the cochlear nucleus. Information is then going to be passed to an area called the superior olivary nucleus, or superior olive for short. It's then going to travel up to the inferior colliculus of the tectum. Then it's going to pass through the medial geniculate nucleus of the thalamus. And then finally, it will make its way to the primary auditory cortex, where we become consciously aware of the sound. So any damage along this pathway, including damage to hair cells or the cochlea, would cause sensorineural hearing loss. Number 8, which type of hearing loss does Grandpa Carl most likely have? So here's a summary of the different types of hearing loss. So anything that stops the sound being conducted to the inner ear is conductive hearing loss. And then anything that damages the nerves or the hair cells is sensorineural hearing loss. Then there are a few things that can cause a mix of the two. Since Grandpa Carl had problems hearing high-frequency sounds, he was older, and since he had a career around loud machinery that likely damaged the hair cells, he most likely had sensorineural hearing loss. So last little section here, some food for thought. So these are just some questions some people wonder about. So why does airplane food have a reputation for tasting bad? So the pressurized cabin atmosphere in a plane can make your taste buds not function normally. Perceptions of sweetness and saltiness can drop by up to 30% at high altitudes. And decreased humidity in the pressurized cabin can also dry out the olfactory lining, which will dull your sense of taste, since olfaction is a large part of taste. Therefore, the food just doesn't taste like it would down on the ground under normal conditions. Why do most people hate to hear their own voice on a recording, including Dr. Sawyer? You normally hear your voice in two ways. So sound waves are conducted through the air, so they come out of your mouth and then are conducted around into your ear through the external acoustic meatus. Like this is the same way that everyone else hears your voice. But When we talk ourselves, we also have sound waves conducted through the bones of our skull that come from vibrations of the vocal cords, and only we can hear this aspect of our voice. So the bone conduction that we hear when we talk makes our perception of our own voice as having a fuller, deeper quality. So when we listen to a recording of ourselves, we're only hearing the air-conducted sound. We're not hearing the bone-conducted sound. So our voice sounds different than we're used to hearing. So don't think about it too much, but the way your voice sounds on a recording is how other people hear you all the time because they're getting your voice without the bone-conducted sound. Why does food taste bad after brushing your teeth? Toothpaste contains a chemical called sodium lauryl sulfate. They add this to toothpaste to create a foam and to make the paste easier to spread. But sodium lauryl sulfate also suppresses your sweet taste receptors and enhances your bitter taste receptors. So for a short time after brushing your teeth, you have a reduced ability to sense sweetness and an enhanced ability to sense bitter flavors, making most foods taste differently than you're used to. And because of the enhancement in bitter flavors, we usually think they taste bad. And finally, why are blood vessels in the eyes more visible when we are tired? So when you're tired, you don't blink as much. And then without the normal level of lubrication provided by blinking, the ocular surface can become drier than normal. And this can cause mild inflammation of the sclera, which then results in dilation of blood vessels in the sclera, making them more visible. And that is the end of the Chapter 17 activity.